Welcome to another exciting episode of AP Computer Science. Be sure to have writing utensils handy to take notes. Often the items added to a queue have a priority associated with them. This priority determines the order in which they exit the queue. Highest priority items are removed first. In this curriculum, the convention will be followed that the smallest value has the highest priority. For example, consider the software that manages a printer. In general, it's possible for users to submit documents for printing much more quickly than it is possible to print them. A simple solution is to place the documents in a FIFO queue. In a sense, this is fair, because the documents are printed on a first-come, first-served basis. However, a user has submitted a short document for printing will experience a long delay when much longer documents are already in the queue. An alternative solution is to use a priority queue in which the shorter a document, the higher its priority. By printing the shortest document first, the level of frustration experienced by the users is reduced. In fact, it can be shown that printing documents in the order of their length minimizes the average time a user waits for the document. We can use a tree structure to keep track of items in a priority queue, which generally provides an O log n performance for both insertion and deletion. Unfortunately, if the tree becomes unbalanced, performance will degrade to an ON in worst cases. There is a structure that will provide guaranteed O log n performance for both insertion and deletion, and it's called heap. Heaps are based on the notion of a complete tree. A binary tree is completely full if all of its levels are filled with nodes. A binary tree is completely full if it has a height h and has 2 to the h minus 1 nodes. Each level contains twice as many nodes as the preceding level. A binary tree is termed complete if it has no gaps on any level. The last level may have some missing leaves on the right as shown below. A heap is a binary tree that satisfies two conditions. It's a complete tree, and the value in each node does not exceed any value on the node's left or right subtrees. Heaps are allowed to have more than one data item with the same value, and the values in the left subtree do not have to be ranked lower than the values in the right subtree. A heap can be used as a priority queue. The highest priority item is at the root and is trivially found. But if the root is deleted, we are left with two subtrees and we must efficiently recreate a single tree with heap property. The value of the heap structure is that we can both extract the highest priority item and insert a new item in O log n time. Removing an item from a priority queue is straightforward if the queue is represented by a binary heap. The next item to leave the queue will always be at the top, or the root, of the heap. The shape of the heap is restored by removing the last leaf and placing it into the root. For the heap shown, the position that must become empty is the one occupied by the 87. This is placed in the vacant root position. This has violated the condition that the root must be greater than each of its children. To repair the order, we apply the heap procedure from which the value of the root moves down the heap until it falls into place. At each step of the value, 87 is swapped with its smaller child. The heap priority still has not been restored to the left subtree, so again interchange the 87 with the smaller of its children. We need to make at most h interchanges of the root of a subtree with one of its children to fully restore the heap property. Thus, deletion from a heap is O log n. To add an item to a heap, we follow the reverse procedure. First, we add a new node as the last leaf, and then apply a reheap up procedure to restore the ordering property of the heap. Reheap up moves the new node from the tree, swapping places with the parent until the order is restored. For example, adding the value 9 to the original heap would result in the following sequence of steps. Again, we require O log n exchanges. The properties of a complete tree lead to a very efficient storage mechanism using n sequential locations in an array. An important benefit of the array representation is that we can move around the tree, from a parent to a child or from a child to a parent by simple arithmetic. If we number the nodes from 1 at the root, then the left and right child of a node I, if they are present, are 2i and 2i plus 1. The parent of a node is I at I divided by 2, truncated to an integer. If items is the array, the root corresponds to items 1. Subsequent slots in the array store the nodes at each consecutive level from left to right. In a Java implementation, it is convenient to leave items 0 unused. With the numbering of nodes, the children of the node items I can be found in items 2 times I and items 2 times I plus 1, and the parent of items I is in items I divided by 2. The AP subset requires students to know the following methods for java.util.priorityQueue. Void add inserts items into the priority queue. Boolean is empty returns true if the priority queue has no elements. Object peek returns the next element without removing it. Object remove returns and removes the next element according to its given priority. The priority is determined by the compare_to method. Therefore, all elements added to the priority queue must implement the comparable interface. The element with the lowest value in compare_to will be returned. To declare a reference variable for a priority queue, do the following. Here's a short example showing how to create, populate, and deconstruct a priority queue. The output prints 1 to 5 twice. This is because the priority queue will insert the elements it receives in the order from their priority rather than the order that they received.